Four different types of energy states, right? What are that? Translation energy, or we can also, the changes occur in that state, that is called translation state. And second one is the rotational energy. That is called rotational change. And third one is
vibrational
change, or vibrational energy, that causes the vibrational change. And fourth one is the electronic energy. Electronic state. Right. Then when we coming to the highest energy state is the electronic state. This is the ground state. When you take any object, any molecule, any atom, if it is in the ground state, this is the ground state. This ground state can be represented with the S naught. Okay. This S naught is also, S naught is equal to E naught. That is, E naught is the ground state electronic state. Ground state electronic state. Same. V naught, ground state vibrational state. R naught, ground state of that particular electronic energy, rotational ground states, and translation state. These are the four states are equal to same S naught. That means at the ground state, these are all zero, V zeros. Now, suppose when you are providing energy, the electron is excited to from S naught to next excited state. This is called first excited state or excited state. This is the ground state. This is the excited state. Now, this is equal to E1, excited state 1. And in this between, there is a several states of vibrational states. This is the V0 it is equal to the V0, and this is the V1, V2, V3, and so on. N number of vibrational states. N number of vibrational state. Now, as we discussed, this is the total ground state where we can see the ground state electronic state, ground state vibrational state, ground state rotational state, ground state translation state. Right. Now, in between these, any vibration state, between two vibrational state, there is a several number of, not only V0 to V1, V1 to V2, V2 to V3, V3 to V4, V4 to Vn, and Vn minus 1 to Vn. Right? There is a several rotational levels. Suppose if I am going to take this in enlarge, this is the enlarged one, right? So I'm taking this one is the enlarge. This is the E naught state. Okay, this is the V1 state. At the level, we have the V0. And in between these two, there is a several levels of rotational levels. Several levels of rotational levels. Okay. And this is the V1, V2, and so on. Sorry, no, Vn. V2 and V and so on. sorry, rotational levels. Right. This is the R1, R2, and so on. The rotational level Rn. Okay. Now, if you take these R02, or V02, or E02, R1, I'm going to enlarge it. The rotational level. In between the rotational levels. I'm going to enlarge it. This is the E0 or V0 or R0. From this level, we have several translation levels, T1 and T2 and so on, Tn. This is the R1. That means, look at here. In between the two electronic excited states, several vibrational levels. In between the two vibrational levels, several rotational levels. In between the two rotational levels, several translational levels. That means when we compare the energy, electronic excited states are having the great energy, then the vibrational level, right? Then vibrational level is having a great energy, then the rotational level. Generally, we can show it the rotational level in the small r, rotational level, then it is the translation level. Right? This is the order of energy of each level which are occurred in nature. But especially when you coming to these levels, translation level, if any object or any molecule, we just create any small disturbance, it causes the rotational excitations. Sorry, translation excitations. That involving the translation level changes, translation levels. Therefore, these translation energies excitation will not consider for any study. These translation energy levels will not consider for any study. Then our concern is only electronic excited state, vibrational energy excited state, and rotational level. These changes are involving the considerable energy changes of the state of the object or of molecule. Therefore, these three are considered for this study. Right now, these are important to understand the Jablonski diagram. Now, coming to Jablonski diagram. Yes, as we discussed earlier, this is the ground state, singlet state, ground state, singlet state. This ground state, singlet state is existing with ground states of electronic states, ground state of vibrational, and ground state of rotational level. Ground state of rotational level. Right? Now, here some electron is there or some molecule is there. We are providing the energy. The providing energy means increasing the energy like this. If this is the indicator of arrow, increasing the energy. Okay. Now, its next excited electronic excitation state is this one is called S1. Next electronic excited state is suppose it may have the some more larger energy, but I am taking like this. This is S2. S1 and S2. Now, whenever we are providing the electrons, this will be excited to the next level of this energy state. This is equal to, this state is equal to somewhat the vibrational level, some X state, vibrational X state, Vx level. Then, we have several things, several vibrational levels. These are the vibrational level. Now, this S1 is equal to this S1 is equal to is existing with first excited state, first excited state of electronic level, that is indicated with the E1, that is indicated with the E1, or first excited state of vibrational 1, first excited state. No. First excited state, it is not showing like this. First excited state of electronic with V naught state or R naught state. R naught state. Look at here. Here also rotational levels are there. Suppose this is the V1, this is the V0, this is the R1, R0. There is a rotational level R1 is like R1 is there like this. Okay. Now this excitation of the molecule from S1 to S0 to S1 of some Vx level. Okay, this is the electronic excitation. This is called electronic excitation, or simply called absorption of radiation, then it gets excited. Suppose the molecule A is there, we are providing some energy or irradiated with, then it gets excited. This is the electronic, it is shown with the A star. That means A star means excited state. That excited state reaches to what position? Some we believe we taken it as S1 state of Vx state or Vx state of S1. Vx state of S1. First excited state, some vibrational level 2, it excited. After excitation, this is the excited state. Now the process is started. Deactivation is started. Then deactivation can take place in several ways. Deactivation says right. Suppose this is the activated state, it will be deactivated to again some leaving the light, that means emitting the light, absorption and emission, emitting the light, or leaving the heat energy, then it gets to ground state. Right? Simply, how can you say that a generalized reaction? Suppose it is both are the forward and backward reaction. In the forward reaction, thermal or photochemical condition, it leads to produce activated state, and deactivation leads to evolving the heat or light. This is the deactivation. During this deactivation, that molecule may reach to several states, several states, and the deactivation is of several types. What are the several types? Suppose, as we see here, the S1 state of vibration some level is reached. From this vibrational level to it deactivated to some V naught of S1. The first vibrational state of S1 state to it will be deexcited. During this deactivation, this will be indicated with the arrow, a wavy arrow. Wavy arrow indicates that liberation of heat. The wave arrow I am showing like this. It indicates heat energy will be released. Heat energy is emitting. Heat energy emission. Right? Now, what is the state or what it is called? This is called vibrational cascade. Vibrational cascade. What is VC? The VC is first level, first deactivation is some vibrational level to another vibrational level. Deactivation is called vibrational cascade. vibrational cascade. Okay, what's happening in this? Some Vx state of S12, it will be deactivated to, or some V0 state of S1. This is vibrational cascade. Vibrational cascade. Or suppose another upper level, it will be on a deactivation of that molecule, it reaches to some S2 level, second excited state, upper excited state. In that also some it is reached to Vy level of vibrational level, Y level of S2 state 2. It deactivated to V1 of S2. This is also vibrational cascade. Vibrational cascade. After reaching the to this state, this is the somewhat V0 state. It reaches to the molecule from this position. From here to, it may deactivate it in several ways. How? This is the absorption, first one. Absorption. This is the vibrational cascade. From vibrational cascade of S1 of V0 of S12, it may undergo several kinds of deactivation. What are that? Suppose if it is directly deactivated to the S1 level, sorry, S0 level, this is the wavy arrow. Okay, this is called internal conversion. This is called internal conversion. IC is here. IC is the internal conversion. Internal conversion. Internal conversion. What's happening in internal conversion? Suppose some V0 state of S12 it deactivated to some V0 state of S0. That is called internal conversion. It is called internal conversion. Or either way, suppose the molecule may be excited to upper excited state. Upper excited. Suppose it reaches to some Vx of S2 state, then it will be deactivated to some Vy of S1 state. This is called internal conversion. This is also called internal conversion. Then next, after reaching or either way from this state, this is the one way. Or either way, from this V0 of S1 state 2, it may reaches to some nearby triplet energy by changing its spin. The electron spins may be changed. Then it is also involving the evolution of or emission of light heat energy. Then some V0 to V0 state of T1. V0 of S1 to T1 state. This is called intersystem crossing. This is called intersystem crossing. What is the intersystem crossing here? ISE. Intersystem crossing. What's happening in intersystem crossing? Here, two different steps. Actually, the molecule is in the some vibrational level of S1 state 2. It will be deactivated to the nearby some V0 state of T1, triplet state. This is called singlet state to conversion is. Deactivation is involving singlet state to triplet state. Singlet to T1 triplet state. Triplet state. This is called intersystem cross. Intersystem cross. Right. Next. After reaching the triplet point, Again, it will be reaches to ground state. It will reaches to ground state. That how it is reaching? It may be reaching the ground state by leaving the heat energy. That is one, right? Or it may be directly reaches to the ground state by emitting the light. Light emission. Light emission means we are direct radiation. That's why we are showing it with the straight line. Wavy curve mean wavy we are indicates that it is evolving the heat energy. Here also it will be directly deactivated to ground state from S1 to S0 state. Now here the two kinds of radiations, the three kinds, 1, 2, 3. Again, this is the intersystem crossing, ISC. Okay. Now this one is called phosphorescence from T1 state to S1 state, involving the evolving the light. Phosphorescence. This is the fluorescence. This is the fluorescence. What is the fluorescence and phosphorescence and ISC here? Second way we are listening the two things. Intersystem crossing is also intersystem crossing is also from T1 state, V0 of T1 state to V0 of S0 state. This is also intersystem crossing. Now, what is phosphorescence and fluorescence? First, you look into the fluorescence. Fluorescence. What is fluorescence? It is involving from V0 of S1 state to directly emitting the light, and V0 of S0 state, or some Vx state of S2 to some Vx of S1 state by evolving the light. That is also fluorescence. Next, what is the phosphorescence? Side by side, you can easily understand. Phosphorescence. What is that phosphorescence? Some V0 of T1 state undergo decaying by evolving the light to that is V0 of S1 state. V0 of S2 S0 S0 state. S0 state. This is called phosphorescence. Now, how many kinds of decaying processes are there? Decaying states are there. Vibrational cascade that is involving some vibrational level to another vibrational level of same electronic state, and intersystem crossing, some vibrational level of S1 to some say singlet excitation state to vibrational level of some triplet state, that is the intersystem crossing, or some triplet state of two vibrational level of some triplet state to vibrational level of some singlet state. That is called intersystem crossing. And what is fluorescence? The fluorescence is the decaying of molecule from the first excited state to ground state by evolving or by emitting the light, or from is called fluorescence, or the excited molecule is decaying from the vibrational level of triplet state to vibrational level of ground state by evolving the or by emitting the light. It's called phosphorescence. This is the Jablonski diagram. Especially the Jablonski diagram explains the how the singlet excited state and triplet excited states are generated in the unsaturated carbons which are involved in the photochemical reactions. Okay, Saidulu raised hands. Ask question, please.
సార్ ఈ ఫ్లోరెసెన్స్ అండ్ ఫాస్ఫరెన్స్ రెండు కూడా ఫోటోకెమికల్ కండిషన్ జరుగుతాయి సార్.
రెండు photochemical conditions. Both are photochemical conditions. Both are involving the excitation states, but the excitation states decayings are different. Fluorescence is decaying of the excited level from singlet excited state to ground state in singlet state.
సార్ ఓకే.
In the case of phosphorescence, the decaying of excited state, that is the triplet excited state to ground state singlet state, that is called phosphorescence.
ఓకే సార్. ఓకే సార్, థ్యాంక్ యూ సార్.
Right. Okay. Next, coming to a detailed discussion on inter-system cross. It is generally it is appearing in the theory exams. Right. Here we have the three different types of unsaturated systems in the especially photochemical reaction concern. We will take three kinds of unsaturated system. One is the carbonyl carbons, carbonyl compounds, and another one is aromatic hydrocarbons like benzene, naphthalene. Okay, aromatic hydrocarbons, that is naphthalene, anthracene, phenanthracene, like that, and olefins. Olefins means simple ethylene or 1,3-butadiene conjugated one. Okay. So simply I am taking butadiene. Butadiene, right? Now, first this for the carbonyl compounds, I am considering the benzophenone. For the benzophenone, it is having easily excitable electrons are lone pair of electrons. The electrons which are present on oxygen, these are the non-bonding electrons are there. The non-bonding electrons are easily undergoing excitation. Then the pi and sigma 1, right? Then whenever we are irradiated that compound, then that will be excited to S0 to S1. S0 to S1. That reaches to, right? How this, what is this S0? This is N2 5 star 1. N2 5 star. Next S2 state is there. What is the, yesterday we are already discussed. S2 state is what? 5 to 5 star. S2 is the 5 to 5 star. But whenever we are providing the energy, in most of the cases, carbonyl compounds reaches to S1 position, right? Then these corresponding triplet states. Suppose S2 has the one triplet state, that is nearer to here, that is the T2, somewhat higher energy than the S1, and S1 is having some triplet state. This is T2. Now look at here, the energy gap between this S1 and T2. The energy of S1 and energy of S2, the gap between these two levels are just 69 kilocalories. 69 kilocalories per mole. It's just enough. It's just enough to reach the T2 state by providing the just 410 nanometers of radiation. 410 nanometer of radiation. Then it is simply undergoing the intersystem crossing, because there is no there is no differentiation between the S1 state and T1 state, because the both are having the nearer energy. Both are having the nearer energy. The carbonyl compounds are associated with the high intersystem crossing effect. Due to this is the reason only the carbonyl compounds are associated with the high intersystem crossing efficiency. Therefore, carbonyl compound can easily gets excited to the corresponding triplets. Sorry, this is the S1. T1. This is the T1. Whenever we are irradiated of carbonyl compounds, that easily produces the triplet state of that carbonyl compound. Suppose just take the benzophenone, just you are irradiated with light is with lower intensity, that easily produces excited state. That is a benzophenone excited state. This phenomena is very much helpful for producing the several molecules triplet state. These carbonyl compounds are generally used for the triplet sensitization. Triplet sensitization. Now coming to naphthalines or anthracene. Naphthalines or anthracenes. These are the moderate triplet sensitizers. These are the moderate. This is the efficient triplet sensitizers, carbonyl compounds, and naphthalines, hydrocarbons, aromatic hydrocarbons are moderately triplet sensitizer, because these are having the moderate intersystem crossing efficiency. Suppose this is the ground state of that naphthalene or aromatic hydrocarbons, and these are the excited states. This is the S1 level. This is the S2 level. The gap between the S1 and S2 is also very large. Their corresponding triplet states are, this is the T2, and their corresponding triplet state is the T1, but not nearer, but somewhat it is having the distance. This is like this T1. Right. Look at here. I just mistake here. Actually, the energy state of this one state is 74 kilocalories energy. This is just 69 kilocalories. Look at here, the difference between the 74 minus 69. What is the difference? Just 5 kilocalories. 5 kilocalories. Therefore, the 5 kilocalories difference is the very negligible value. Therefore, this S1 and T1 in the case of carbonyl compounds are almost very near to each other. Due to that reason, the carbonyl compounds are easily producing triplet excited state by undergoing the intersystem crossing. But in the case of aromatic compound, the distance between these two is very large. The distance between these two is very large. When we compare to these two, almost the distance is involving almost 25 kilocalories. 25 kilocalories, the distance. This is also undergoing intersystem crossing, but this crossing efficiency is the moderate. It is the efficient. Why? Because carbonyl compounds are easily used for the triplet sensitizer, but not the aromatic compound. Aromatic compound, they self undergoing the excitation, then it produces the triplet state. That triplet state is only sufficient to convert the corresponding products of that to the aromatic compounds, but that triplet state will not transferable to the other compounds in most of the cases. Due to that reason, aromatic compounds are more rarely used for the triplet sensitization. When you come into butadiene is having the S1 state is this one, and S2 state is this one. Now the triplet state is like this. This is the T1 state. The difference, almost this is the 124, this is the 60 kilocalories. Then it is undergoing the intersystem crossing. to produce the triplet state. But this is very highly impossible because almost 64 kilocalories difference is there. Therefore, this intersystem crossing is prohibited. Very large energy gap is there. Therefore, this intersystem crossing is prohibited. Therefore, in most of the cases in the deactivation, the S1 state gets deactivated to S2 state instead of intersystem crossing. Therefore, carbonyl compounds are more prominently used for the triplet sensitizers. And butadienes are used for the quenchers. Olefins are used for the quenchers. These are the general reacting materials in the compounds. Okay, that is about the intersystem crossing. Photosensitization and triplet energy transfer. Photosensitization, triplet energy transfer. What is the photosensitization? Photosensitization is exciting the molecule. Suppose here carbonyl compound is there, it can easily undergo the excitation whenever we are irradiated. But some molecules they are not get excited even though we are irradiated with light. In such case, we are irradiated the carbonyl compound. These carbonyl compounds will be collide with the reacting substance. That will be the energy with the activated energy present in the carbonyl compound is transferred to the unreacted species. Then it gets excited. Then deactivated carbonyl compound is released out. Then the whatever the compound activated by the carbonyl compound is involving in the reaction. Then finally it produces the product. That is the entire photochemical reaction. In the the process of the reactant get excited by colliding with the activated carbonyl compound is called sensitization or photosensitization. For photosensitization, what we are doing here, first carbonyl compound is irradiated with light. Therefore, the photochemically exciting the carbonyl. After exciting the carbonyl compound, that will be mixed with the reactant. That mixture during the reaction, that will be collide with the reactant. That energy transfer from the carbonyl compound to reacting material. Then that reacting material is undergoing the reaction that leads to produce the product. Okay, this process is called photosensitization. Photosensitization is an important process in organic chemistry. It is a method for producing triplet states in compounds with zero intersystem crossing efficiency. That thing I have said. Whatever the compound which is need to be undergo photochemical reaction, but it will not absorb the photochemical condition or light. Therefore, it is not excited to higher energy level. Therefore, it will not undergoing any reaction. Due to that reason, we need to add external substance for the excitation. That species is called photosensitizer. That process is called photosensitization. When a mixture containing large excess of donor compound with high efficiency. Here, what is the photosensitizer? Photosensitizer is the high efficient intersystem crossing efficiency compound that will be used as photosensitizer. For example, benzophenone. And the acceptor is what? From benzophenone to energy transfer to the reactant. Here the reactant is accepting the activated energy. Therefore, whatever the acceptor here is, most of the cases the acceptors are just simple olefins or aromatic hydrocarbons. Those which are not undergoing the reaction through the triplet state energy to the triplet energy state intermediate. Okay, or transition state. Now, mechanism of photosensitization. Mechanism of sensitization. Okay. Hardly in the photochemistry we have 10 reactions are there. These 10 reactions are, if you learn, you can easily attempt the photochemical reaction questions in the examination. Are those 10, 11 question, 11 reactions will be only discussed because we have the short time. In this short time, we are unable to complete all the 5 units in detailed discussion. I can discuss, but the time is important. If during this time, 2 to 3 days time, we will discuss about the complete photochemical reactions which are involving the important 10 reactions. Okay. This mechanism is also important. Mechanism of photosynthesis. Yeah. This is the donor. What is the donor? That is the photosynthesizing agent. D is the photosynthesizing agent. Whenever we are irradiating with light, it will get excited. The excited state of D, which is shown with the star. Or we can also show with the singlet energy level, D1. The singlet energy level D1. This D1 again undergoes intersystem crossing that leads to formation of triplet state of D. Triplet state of D. This triplet state of D is reacting with the A, that is undergoing the reaction means the A is collide with the D. During this colliding, the energy, triplet state energy will be transferred to the A. Therefore, the A directly excited to triplet state. A directly excited to triplet state, then D becomes activated, deactivated. This activated triplet state may undergo the reaction that leads to the formation of B and C product. Okay, this is the mechanism, general mechanism of photosensitization. General mechanism of photosensitization. Next, when we come into the one example, take the benzophenone. The benzophenone is an example for ketone, carbonyl compound or aromatic ketone. Now, it is irradiated with light at one, a specified frequency of light. No, you can understand that we can irradiate it with different frequencies. Different frequencies gives the different activation states. Okay, based on that, we have the requirement of reaction. We are going to irradiate it with the light. Okay, now this will be gets excited. It reaches to first excited state. The first excited state of benzophenone is showing like this. This is the first excited state of that is N2 5-star excited state. First excited state of benzophenone. Now again, this first excited state, we can also show the straight arrow, but mention that it is undergoing intersystem crossing. Intersystem crossing. Then it leads to formation of a triplet state of benzophenone. What is the triplet state? The triplet state is again N2 5-star triplet state. N2 5-star triplet state. Now this is the activated donor. This is the activated donor D. Right. Now this will be reacting with a triplet state of N2 5-star will be bombarded with the 1,3-butadiene. 1,3-butadiene. This is in the ground state, right? Now it leads to the photosensitization process. Then it leads to formation of a triplet excited state of 1,3-butadiene. Triplet excited state of 1,3-butadiene. How it is happen, I will show you. Right. Then a ground state benzophenone is generated. Later, it is further undergoing the reaction. or other reaction. Okay, this is the general mechanism of photosensitization of a example. Then in this in the above reaction, what's happening? Why it is directly producing the pi to pi star excited state? Why it is generating pi to pi star excited state? Look at here. Pi to pi star excited state, how it will obtain, right? Okay, here. First, this is the energy level diagram I'm showing. The energy level diagram. Now, this is the ground state energy of some S naught state of benzophenone. When we are providing the energy, that will be excited to somewhat higher energy, that is S1 level, when we are providing the light energy. Right. Its corresponding triplet state is like this. It is with 74 calories. It is with 69 kilocalories. Now it is undergoing triplet energy transfer, energy state, intersystem crossing. This is the T1 state. T1 state. Now look at it. This is the olefin 1,3-butadiene, 1,3-butadiene. It is the S naught state of 1,3-butadiene. And the S1 state is like this. Very high energy gap. This is the S1. The excitation from the S naught to S1 is very impossible thing because the energy gap is more. Due to that reason, it will not undergoing photochemical reaction directly. It requires the photosensitization. Now its corresponding triplet state, that is the T2 state. The T2 state is like this. This is the T2 state. T1 state of 1,3-butadiene with the energy 60 kilocalories. 60 kilocalories. Now look at here, the gap between the T1 of carbonyl and T1 of 1,3-butadiene, just a 9 kilocalories difference. When you compare, the T1 is decaying to S naught of benzophenone, is more gap, it requires a higher energy differentiation, but it is the energy difference between the triplet state of carbonyl compound, the triplet state of 1,3-butadiene is very, very little amount difference. Therefore, this will be negligible. Then immediately this triplet energy will be transferred to this T1 state of olefin to get the lower energy transition state to stabilize it. After stabilization, that leads to the formation of the triplet state of that 1,3-butadiene. The triplet state of 1,3-butadiene can undergo the reaction that leads to produce the corresponding cyclization, dimerization, like products. Yes. How this can be explained in another way? If you take the biacetyl, what is the biacetyl? The biacetyl is like this. This is the biacetyl, right? Next, pyrene and naphthalene. Okay. Now here, when you take the three compounds, Look at here. This is the biacetyl and pyrene. Four benzene rings are fused to each other. Four benzene rings are fused to each other. The way the pyrene is existing is the pyrene. Next, what is the naphthalene? You know that. What is the naphthalene? Three rings. The two rings. Naphthalene like this. Okay, this is these three compounds are there. Suppose whenever we are irradiating this three compound mixture, what is we obtain the activated state of the compound? We have irradiating. Suppose you take the vessel around bottom glass, you take biacetyl and pyrene and naphthalene, you take it in the same vessel, irradiated with light. Which one will be obtained? Which one will be obtained? Look at here. First, I am taking the biacetyl here. This is the S0 state of biacetyl, and its corresponding S1 state is like this. This is the S1 state, and its corresponding T1 state is like this. T1 state is like this. Next, you take the pyrene, and corresponding S1 state is like this, somewhat above the biacetyl S1, higher energy than the biacetyl, and you take the T1 state, somewhat the area like this, T1 state. Next, naphthalene. Naphthalene, it will be exited to the first exited state is like this, S1, and the T1 state is like this. Now look at here. Suppose the biacetyl carbonyl is the photosensitizer, and pyrene and naphthalene both are there. Which one triplet state is obtained? You tell me. Which one is the triplet state is obtained? Hello? Follow it, Nara?
Yes, sir.
What is the triplet state? First, this is the photosynthesizer. Now electron is excited from here to here. Sorry, the biacetyl is excited from S0 to S1. Then it is undergoing intersystem crossing. The T1 state of that biacetyl is obtained. Then therefore this T1 state will not come to S0 state of biacetyl. It is undergoing intersystem cross. There's internal conversion from the T1 to T1 of pyrene. Therefore, the pyrene triplet state is obtained instead of naphthalene. Therefore, pyrene triplet state is obtained, then the naphthalene. Right? Understand?
Yes, sir. Yes, sir.
Ma?
So मला
Yeah. Look at here. Look at. I will explain the reaction form. Suppose this is the biacetyl. This is the biacetyl, which is subject to focus radiation. Then it leads to, after excitation and intersystem crossing, it leads to produce the triplet state. After formation of this triplet state is 3 N2 5 star. Then this N2 5 star will bombarding with the pyrene, the 4-member ring pyrene. Okay, then it leads to formation of pyrene triplet state of 5 to 5 star. 5 to 5 star. Along with the AC ground state of biacetyl. Ground state. But there is no formation of naphthalene triplet state. It will not react with suppose it is reacting with the naphthalene. there is no reaction. Sorry, no energy transfer. No triplet energy transfer. Energy transfer. Okay, this is the arrow from here to here. Okay, there is no reaction here, but between the pyrin and triplet state of base that will gives the triplet state of pyrin and ground state of base. That is called triplet energy transfer or photosensitization. Triplet energy transfer or yes,
Photosensitization.
photosensitization or triplet energy transfer. Now, next one is intramolecular triplet energy transfer. Intramolecular triplet energy transfer. What is intramolecular? In the previous one is intermolecular energy transfer. That means two different molecules are undergoing the photosensitization. One of the activated state, one is the ground state is undergoing the bombarding. That leads to the formation of excited state of the reactant. That is called intermolecular triplet energy transfer. But here intramolecular triplet energy transfer. That means the triplet energy is transferred within the molecule. The triplet
Yes.
energy is transferred within the molecule. In our book, one example is given, that is benzophenol derivative, that is naphthyl benzophenol derivative. That within the same molecule, benzophenone is there, naphthalene is there. This is the benzophenone. And it is bridged with some three number of bridged methylene groups and attached with some naphthalene. Naphthalene is there. What's happening? Suppose this is taken as A. Like I will take complete, right? It is irradiated with the light. It is irradiated with the light. What's happening? The first up to the benzophenone fragment get excited. Intersystem crossing also happen at the same step. Up to this species get the triplet state of N2 star. Triplet state of N2 star, and it is bridged with some 3 or 4 of naphthalene is also attached here. The next step, energy transfer. Triplet energy transfer. What's happening? Only benzophenone moiety gets excited. Benzophenone moiety gets excited. Then, in the next step, triplet energy transfer. Triplet energy transfer, intramolecular triplet energy transfer. Triplet energy transfer. Right. Then what's happening? Look at here. Intramolecular triplet energy transfer involving only this part will be excited by gaining the transferred energy from the benzophenone to naphthalene. Then it leads to produce the triplet of 5 to 5 star. Triplet of 5 to 5 star. This is called intramolecular triplet energy. Benzophenone and naphthalene moieties are present in the present in the same molecule. Its absorption of UV light will be composite to give the excitation of up to benzophenone moiety. Then the excited triplet energy state of benzophenone moiety will transfer its energy to the naphthalene. Other examples are also there. We have 4-methyl benzophenone and 1-methyl naphthalene is bridged with the methyl group. When the compound is irradiated selectively at the wavelength of absorption benzophenone, then absorption of benzophenone is undergoes. Then it will give to the phosphorescence. It will give the phosphorescence emission. Then it leads to the formation of 5 to 5 star naphthalene activated state. Then further it is undergoing the further reaction. Okay. This is about the intramolecular triplet energy transfer. Intramolecular photosensitization also we call it as this one. Intramolecular photosensitization or intramolecular triplet energy transfer. Then configuration of T1 state in carbonyl compound. Configuration of triplet energy state of T1 state in the carbonyl compound. Just a minute, I will take some water. Will come in by 1 2 minutes. Next topic is configuration of T1 state in carbonyl compound. Configuration of T1 state in carbonyl compound. Configuration of T1 state in carbonyl compound. That means configuration means whether it is the 5 to 5 star or N to 5 star. We need to decide it. We need to decide it. That is the thing we are going to learn. Right. The configuration of low-lying triplet state in ketone is T1 state. Need not to be the same as that of the first excited singlet state. In carbonyl compounds, S1 state is of N to 5 star configuration, and S2 state is the 5 to 5 star. S2 state is the 5 to 5 star configuration, whereas its corresponding triplet state is the 5 to 5 star triplet state. Whereas the T1 may be the N to 5 star or 5 to 5 star, because sometimes the gap between the S1 and S2 may be larger. S1 may be S1 and S2 may be larger. But the T1 sometimes very below than the S1 state, and the T2 state sometimes very nearer to the just below to the S1 state. Due to that reason, the triplet state the energy transfer from the singlet energy to triplet energy easily to the T2 state instead of T1 state. Like, for example, in some cases, in most of the general cases, look at here. Suppose this is the carbonyl compound. It may involving, this is the S1 state, and this is the S1 state. And corresponding S2 state is like this. Look at here. From the excitation S1, S0 to S1 is the N25 star. Or sometimes the energy is excited from S0 to S2 is the 5 to 5 star. 5 to 5 star. Then, how can you understand about the triplet states? Here there are several ways. Suppose this is the N25 star state. N25 star state. Therefore, the triplet energy may be very nearer to the energy gap is very near. That is, this is the singlet N25 star. This is the triplet N25 star. In some cases. At the same time, this is the T1 state. And at the T2 state is triplet state of 5 to 5 star. This is the most of the time we see. But some cases, when the what are the some cases? In general, it will be appear like this. What are the some cases? If the extended conjugation is there, that means the number of conjugated double bonds are increasing. This configuration will be changed to this is the S0, this is the S1, this is the S2. Then the T2 becomes here, the T1 becomes here. Now, whenever the N25 star is occurred, N25 star, that is singlet N25 star state is occurred, what's happening? The intersystem crossing is happened to T2 state. What is this T2 state? Triplet of 5 to 5 state. When it will be happen in the case of extended conjugation, or sometimes a suitably substituted carbonyl compound. In the case of suitably substituted carbonyl compounds and with extended conjugation with the carbonyl compound. In such case, it will be happen. In general case, we seen like this. In general case, we seen like this. It is will be, for example, for this case, the benzophenone or estophenone. This is estophenone and benzophenone. For this example, we have several examples are there. That is Michelin ketones, T-para dimethyl amino, C6H4 and C6H4 biphenyl derivative. This is called Michelin ketone. This name is Michelin ketone. MICHLR, Michelin ketone, and some acetone naphthalene, 1-naphthaldehyde, phenyl benzophenone, paraphenyl benzophenone, like these compounds will show this kind of behavior. That means it involving the extended conjugation. This is the benzophenone, suppose. This para substituted phenyl, para diphenyl, like this. What's happening? Suppose only one benzophenone, it is having 6 conjugated double bonds. But number of 2, 5 pairings are increased. 6 plus 6, 12 conjugated double bonds are there. Therefore, the conjugation is increases. The T2 energy level becomes energy gap between the S1 and T2 becomes decreases. Therefore, this type of arrangement or configuration will be seen. Right. Next, last topic in the reactivity of excited state. Reactivity of excited state. That depends. Actually, we can't say theoretically, but some we have the rule of thumbs are there. We need to remember. Right. Reactivity of excited state. Reactivity of excited state. What's happening? If you take a carbonyl compound, for carbonyl compounds, it shows the singlet of N2 pi star and triplet of N2 pi star state. Okay. Right. In this case, in such case, we look into here and these excited states involving this is the carbonyl compound. There is no disturbance in the pi electrons. What are the electrons are disturbed in this case? These n electrons. One of the electron will be excited to higher energy level. Therefore, in this oxygen, electron density becomes decreases. Electron density becomes decreases. Electron density becomes decreases. Once the electron density decreases, electron into excited state, and on the oxygen only one unpaired electron is there. Therefore, it behaves like a free radical, and its nature is electron deficient. Therefore, it undergoes electrophilic reactions, and free radical reactions. Free radical reactions like hydrogen abstraction reaction. And next kind of excited state, like only 5 bonds are there. No n electrons are there. Only 5 bonds are there. In such case, 5 to 5 star singlet excited state, and 5 to 5 star triplet state. What's happening? The formation of these excited state involving the excitation of pi electron. There is no disturbance in the n electron. Sometimes n electrons are absent. Therefore, electrons will be excited from the pi orbital to excited state, which leads to increasing the density on the carbon, that leads to undergoing the nucleophilic reactions, but it is not less effective in the hydrogen abstraction reaction. 5 to 5 star reactions are 5 to 5 star reactions are less efficient in the hydrogen abstraction reactions, but it generally participate in the nucleophile initiating reaction. Therefore, because these five bond is act as a nucleophile, therefore initiate the nucleophilic reactions. That's why it is undergoing nucleophilic additions. Okay, addition kind of reactions, it is participating. Okay, this is about the reactivity of excited states. Reactivity of excited state. Right? Up to this, the first unit is completed. Tomorrow, well, not tomorrow, in the next working class, we'll discuss about the photochemistry of carbonyl compounds. In this, we have just Petronovic reaction, Norris type cleavage are very important. Those things we are discussing in the next Saturday class. Okay? Do you have any doubts? You can ask me. In the time, I will clear. Is there any doubts?
No, sir, no doubts.
No doubts. That much easier, this topic. There is no doubts. Okay, if it is understand, very good, very well. That thing I need also. Okay.
Okay, sir.
Thank you. I'm leaving the class.
Thank you. Thank you.
हो गया क्लास हो गया